everybody. All right, gang, good afternoon. Welcome back to Calc 2. Sorry about the little delay here. My cats have decided to take up some real animus towards one of the very friendly neighborhood strays that likes to come around and say hi to us, or breaking up cat fights. Today, we're going to continue talking about sequences. I did go ahead and release your homework for this week, and I've set it to be due next Thursday, so you have a full week to work on it, because I did not remember to push that on Tuesday. But that's okay, because there's really quite a bit more that we need to say about sequences before you can actually dig in. It's kind of a wholly fresh topic for us. So let's get to it. Today is the 25th. And today we're going to do more work with sequences, which again is section 11.1. As much as I can show you, and as much as I want to show you everything that there is about sequences, it's really not possible for me to show you everything there is to know about sequences. I'll show you everything I'm going to test you on and everything I feel like you need to know right now. But I want to just encourage you guys to do some independent reading about sequences. Google is your friend here. The textbook is okay. YouTube, Google, whatever. And then there's a special text I would refer you to if you're feeling advantageous. Rudin wrote a book called Principles of Mathematical Analysis. Principles, this is sometimes called Baby Rudin, has a bunch of different shit in it. Let me see if I actually know where I have copied this is on. So this is a big book, and it's a little bit intimidating, but I wouldn't recommend that anybody read all of this unless they really want to. But what you really should consider reading here are the first 3 chapters. If you want to understand calculus in any sort of deep way, this is kind of the standard advanced calculus textbook, or like baby real analysis textbook. And chapter 3 is fairly tractable. You'll learn in chapters 1 and 2 some point set topology and notions of metric space, some notation that grown-up math people like to use when they talk about grown-up math. But it's in chapter 3 where you'll get to see a careful treatment of sequences, a genuinely rigorous treatment of sequences. It's a great book. This is still the standard book for teaching analysis. If I had to teach a first graduate course or an advanced undergraduate course in real analysis, this would be the book I would use. And specifically the chapter on sequences and series is really, really good. So if you want a real deep understanding of this stuff, Rudin is the way to go. Baby Rudin, Blue Rudin, also called, its title is Principles of Mathematical Analysis. So this is the book, and you get the idea, right? They're showing, like, you've got some sequences here, and they ask you some fun things about them. Here's a theorem, right? So let this be a sequence in a metric space. Show that this converges to a point in that metric space if and only if every little neighborhood of P contains all but finitely many of the terms of the sequence. This is sort of what I was saying to you guys the other day, right? If you have an epsilon window about L, if you have that, you think your limit is here and you draw an epsilon window about that window, the sequence converges if and only if all except for finitely many of the terms are in that window. So this theorem is actually one of the characterizations I gave you guys. And then there's a few other things here, like a sequence can have only one limit. If you have a sequence that converges to two different, to two things, P and P prime, then P and P prime have to be the same. Any convergent sequence is automatically bounded. I'll be talking to you about what it means for a sequence to be bounded today. But this is really good shit. And if you are interested in this, I can encourage you as much as possible. I can go as far as, not that. Don't tell anybody I did this. I'm getting you a copy. So if you want baby Rudin, just don't tell anyone you got it from me. All right. Of course, Google and YouTube and our textbook are going to have more digestible treatments of sequences, but Rudin is the kind of world standard right now. So last time we defined what a sequence is. We looked at a bunch of examples. We saw some graphs, and we got as far as defining what it means for a sequence to converge, and then looking at a few different examples, simple sequences. I wanted to start going through the theorems that connect sequences to things that we know about. And the first one, kind of the most useful theorem relating sequences to, I'll just call them regular functions. Functions as we're used to thinking about them. The book has this theorem, and it just says if the sequence AN kind of comes from a function of a real variable in the sense that AN is equal to f of n for a known function f of x, then the limit as n goes to infinity of AN is equal to the limit as x goes to infinity of f of x. So the other day, you'll remember somebody asked, when we wanted to take this limit of the sequence n over n plus 1, should we use L'Hopital's rule? And I said, well, kind of, but you sort of need a special workaround. So here is the workaround. Ethan's comment in chat there is worthy of address as well. So reading mathematics is super difficult, period. The trick to reading mathematics is you don't use these, you use this, right? You cannot read math with these. These don't, they're just, it's not good enough. To read mathematics, you need to write it down as you go. And you need to pause from the book. You write down a sentence or two or a line or two, then you push the book away, you look at your writing, and you work a little bit on your own, and you see what you're getting and what you're starting to think, and then you look back to the book to see if you agree with what they have. The brain and the eyes are not the skills for reading mathematics. It really is a pencil and paper thing more than anything else. And that's true of all math books. And it's true not just of calculus, but if I wanted to start reading any specific subject in mathematics, that's how I have to do it too. You got the paper here, and then you got your own like notepad here, or your book here and your notepad here, and you spend more time here really than you do here.
Professor, remember when you said to leave 3 blank pages to write theorems?
So this
would this one be sequences?
Mm-hmm. Yep. So in our page on convergence results for sequences, the first thing we should have up there is that definition of convergence for a sequence. Right? If the limit exists and is finite, then we say the sequence converges to that limit. This would be your second one. This is, again, the tool that's going to allow us to connect sequences to real variable functions, and hence let us use things like L'Hopital's rule. So let me show you what I mean. First example here, I won't use L'Hopital's rule, but let's say, you know, investigate the convergence of the sequence an, and from 0 to infinity, defined by the rule an is equal to the inverse tangent of n. We all know how I love the inverse tangent function. The trick to investigating the convergence of a sequence is just to look at the limit, right? If the limit as n goes to infinity of an exists and is finite, then we would say, okay, well then an is a convergent sequence. In this case, that means looking at the limit as n goes to infinity of the inverse tangent of n. And at a glance, it's really not obvious what's going on there because there isn't any sort of algebra I can do with that. Like that renormalization trick sure as shit isn't going to help here because there's no way to kind of penetrate the inverse tangent function algebraically. But if I relate the sequence to the function inverse tangent of x, and I know that arctan of x looks like this. Then my sequence is necessarily trapped along the graph of this function. That's really what this is saying, right? So my sequence is a bunch of dots but just because of the way the sequence is defined, right? It's like inverse tangent of 1, inverse tangent of 2, inverse tangent of 3, 4, 5, 6, 7, and so on. Even though I don't know anything about, you know, like algebra stuff that I can do here, I do know what the limit as x goes to infinity of the inverse tangent of x is, right? That's coming from the horizontal asymptotes, or really just horizontal asymptote, one of them, of the arctan function. So I would say, okay, I know that this, because an is inverse tangent of n, this would be the same as the limit as x goes to infinity of the inverse tangent of x. And that is something I know. I know that this is pi over 2 because f of x equals tan inverse x has y equals pi over 2 as a horizontal asymptote approached as x goes to infinity.
Okay, so how did you relate a sub n to tan the inverse of tangent? Like, where did that come from?
So we were told that that was the sequence, that the sequence an is.
Sorry, I thought you meant sub an always equals inverse of tangent.
Yeah,
okay,
just in this. So like this is the statement of the problem right here.
All right.
And then everything below is the solution. So they said, investigate the convergence of the sequence an defined by the rule an equals arctan n. So I know that means I need to take the limit of the an's. And since an is arctan n, that means I'm taking limit as n goes to infinity of arctan n. And then I think, well, shit, I don't know what to do with this. but I know what the inverse tangent graph looks like as a function of a continuous variable. It's this orange graph. And since my function, my sequence is inverse tangent of n, its graph is just dots along that orange graph, which means wherever the orange goes, the black dots must go as well. And since the orange, as we run off to the right, goes to pi over 2, that's this going to pi over 2, I know that the sequence has to go towards pi over 2 as well. So here I would say, therefore, the sequence converges to pi over 2. That would be my final answer here. But the real important stuff is the work and the understanding where this is going and why. So again, what this theorem is saying is that if your sequence comes from a continuous variable function, like a regular function that we're used to dealing with, like f of x equals whatever, some function that we fucked around with in the past, if you can find the horizontal asymptote for that function, that's equivalent to finding the limit of the sequence, right? This thing up here, if you want, you could say this is equal to the horizontal asymptote for f of x as x goes to positive infinity. But this has other utility also. This is how we justify the use of L'Hopital's rule for sequences. Before I do that, I've got one other example of a kind of family of sequences that we can handle in this way. So before I move on, any questions on this guy? Okay. Let's see. Maybe I should, let me share one more theorem with you here. And then another example. This guy just says, when n to infinity of an equals 0 is equivalent to, or happens if and only if, the lim n to infinity of the absolute value of an equals 0. So a sequence going to 0 is equivalent to saying the absolute value of that sequence goes to 0. This is intuitively appealing, right? The only thing whose absolute value is 0 is 0. The proof here is utterly trivial. The lim as n goes to infinity of the absolute value of an is equal to the absolute value of the lim as n goes to infinity of an. So if lim n to infinity an equals 0, then this piece, then lim n to infinity abs an equals abs lim n to infinity an equals abs 0 equals 0. And conversely, if lim n to infinity absolute value of an equals 0, then the limit as n goes to infinity of an can be bounded above by, I should say above and below by abs an less than or equal to an less than or equal to positive abs an. And then you take limits everywhere, which implies n to infinity negative abs an less than or equal to n to infinity an itself, which is less than or equal to n to infinity abs an. And the outer two guys are going to 0. So this is 0 is less than or equal to when n to infinity an is less than or equal to 0. And that means that this guy has to be 0.
Does that say which implies?
Yes, sir. So I'm showing you the proof here just because the proof is very easy. But the theorem has a great deal of utility. So the idea is, if your sequence goes to 0, then so does its absolute value. And if the absolute value goes to 0, then kind of by the squeeze theorem, right? We can bound our sequence above and below by the negative of its absolute value and the positive of its absolute value, then take limits everywhere. And I get that my guy has to go to 0 as well. Again, the proof, don't stress too much about the proof. I'll show you proofs when they're easy or insightful. This one happens to be easy, although not necessarily insightful. The fun here is that I can now use this theorem to get lots of limits of sequences that would otherwise be a little bit difficult to justify. So let me show you what I mean. One of the sequences we looked at the other day but didn't look at the convergence result for was kind of an oscillating harmonic type sequence. Now, this was one we listed the first 5 terms of, and we looked at the graph. So if I want to investigate the convergence of this sequence, that means I need to look at the limit of this sequence. The limit as n goes to infinity of an here is the limit as n goes to infinity of -1 to the n plus 1 over n. And this is another case where it's not super easy to say what's going on. The top, as n goes to infinity, -1 to the n plus 1, that just goes back and forth between 1 and -1, 1 and -1. He doesn't exist. And the bottom is like infinity. So this is kind of like not super easy to say what's going on. But if you look at the limit of the absolute value sequence instead, that's the absolute value of -1 to the n plus 1 over n, still with our limit as n goes to infinity. Now this I can start to play around with algebraically. There's stuff I can do here. Remember, absolute values play nice with multiplication. They play nice with division. And they play nice with powers in the sense that, like this. So these are some nifty rules for the absolute value. And we'll be using these somewhat often, not just in this section, but in later sections. So if these aren't things that you've internalized in your past, now is a good moment to do so. This means I can start diving in here and picking this apart. I can say this is lim n to infinity, absolute value of -1 to the n plus 1 divided by the absolute value of n. Using this second rule here. N is going to positive infinity. So the absolute value of n downstairs is just n. N is certainly a positive number. This is lim n to infinity. Downstairs here is just n. Upstairs, I can use the third rule here and say, okay, well, -1 to some power, all in absolute values, is the same as the absolute value of -1 to that power. But the absolute value of -1 is just 1. So this is lim n to infinity, 1 to the n plus 1 over n, like this. But now 1 to the 1, 1 to the 2, 1 to the 3, 1 to the 4, 1 to the 5, they're all 1. The numerator here is always just 1. So this is lim n to infinity, 1 over n, which is 1 over infinity, which is 0. So even though the original limit, the limit of the original sequence is kind of hard to get at because of this upstairs piece not having a limit, he's a DNE. When you take absolute values, the thing you get is just 1 over n. And 1 over n, we know that goes to 0. So since lim n to infinity, absolute value of an equals 0, we know lim n to infinity an equals 0 also. This is by our theorem. Therefore,
so can you just casually apply like absolute values to any of these sorts of sequences, or does it have to be specific ones?
you can always check, right? So if you're having a hard time wrangling your sequence and you suspect that that sequence might have limit 0, then it's a wise thing to look at the absolute value sequence instead, especially if your sequence is like blinking back and forth between positive and negative or something like that.
Okay, okay.
Thus, our sequence n equals -1 to the n plus 1 over n converges to 0. All right, so everybody's following the logic here, yeah? Couldn't figure out what my sequence did, but when I took absolute values, that guy went to 0. Since the absolute value of my sequence goes to 0, by the theorem we just proved, our sequence itself must go to 0. So the limit of our sequence does exist and is finite. It's 0. So that sequence is a convergent sequence. Specifically, we'd say it converges to 0. That's one of the ways this theorem, where did you go? That's one of the ways this theorem can be useful. I got 2 more examples for you, kind of combining the theorems that we've seen so far. First, any questions on what we did here?
How did you go from the from the absolute value, that right there, yeah, above
Here to here?
to, yeah.
So the absolute value of n is just n because n is positive, right? For sequences, n is always a positive integer, a non-negative integer. And then the top, I'm using this rule. It says the absolute value of a to the b is the same as the absolute value of a raised to the b. So powers can pop out of absolute values. That's this third rule. So in here I have -1 to the n plus 1, all inside an absolute value. That's the same as the absolute value of -1 raised to the power of n plus 1. So like here, think of a as -1 and b as n plus 1. And this is like this. And this is this.
All right, got you.
The proofs of these, by the way, if you ever, while I'm showing you guys books that all future mathematicians need to read, let me see if I have this. The proofs of these sort of things you will find in, I don't, do I? All right, here, sorry, I've got a hard copy of it. If you want to start proving algebra properties, you want to really look into why algebra things are true, this is the book. It's the best one. Holy shit, you can get this. Oh, it's rent. Yeah, okay, you can get a used copy for 70 bucks. This is all the algebra you'll ever need. And I mean that. Not just algebra of real numbers, but like big boy algebra, abstract algebra in general. And you prove, among many other things, properties like this. All right. More examples of sequences and how we can use theorems to help us with sequences. A big family of sequences are called geometric sequences. And you probably saw these in your pre-calculus class, at least a little bit. But let me remind you. A geometric sequence is a sequence in which one passes from a given term to the next term by multiplying by a fixed constant. Another way of saying this, these can always, fixed constant called the common ratio. These can always be written in the form an equals a0 times r to the n, where n is greater than or equal to 0. All right, so a geometric sequence, for example, let's find a formula for sequence an whose first few terms are, how about 2? And then let's do -4/3, and then +8/9, and then -16/27, and so on, and investigate its convergence. Okay. So I like to let geometric sequences start at n equals 0. It makes the formulas nicer. I think your textbook has them start at 1, which just makes this n swap to an n-1. But the formula is pretty like this. So I would call this A0. I would call this A1. I would call this A2. I would call this A3, and so on. What do you notice about going from A0 to A1, A1 to A2, A2 to A3?
They're all multiplied by 2/3.
Good. Yeah, we multiply by -2/3 to go from here to here. And we multiply by 2/3 to go from here to here. We multiply by negative 2/3 to go from here to here. So the common ratio, so what we would say is AN is a geometric sequence with common ratio R equals negative 2/3. So I can write down the formula for AN. It will be A0, which is 2 times R, which is negative 2/3 to the N. And this makes sense, right? I start with 2. And if I want to get to like the third guy, I have to multiply by 2/3 1, 2, 3 times. So that means I take 2 and I multiply by 2/3 to the 3. So this is the formula for the sequence whose terms start like this, and it's called a geometric sequence. Any sequence that works like this, where you go from one term to the next by multiplying by a fixed constant, the same constant, to go from A2 to A3 or A7 to A8 or A0 to A1, same constant, it's called geometric. And you can always write them in this way. But you want to make sure that you say where n is starting. Because if n started at 1, then the first term wouldn't match for what you get with this. But if n starts at 0, then these match. Any questions about how we arrived at this? Okay, so then the convergence thing, we need to calculate the limit as n goes to infinity of AN. And to do that means to calculate the limit as n goes to infinity of 2 times negative 2/3 to the n. And now the 2 out here is a constant multiple. He is of no consequence. He's like 2, he can pop out. 2 times lim n to infinity, negative 2/3 to the n. But this is tricky, right? This is not obvious, the negative 2/3 to the n thing.
But the absolute value is still less than 1, so it would still converge.
That's where we're going, yeah, so we will get there. How do I say this? So if you wanted to try to split this up, you could write this as, the 2 is still here, so let me continue over here, equals 2 times lim n to infinity. This is the same as negative 1 times 2 all over 3 to the n, right? So this would be 2 times lim n to infinity, negative 1 to the n times 2 to the n over 3 to the n. And each of these pieces has their own challenges. This piece on its own, as n goes to infinity, would give me a dne. This piece on its own, as n goes to infinity, would give me infinity. And this piece on its own, as n goes to infinity, would give me infinity. So I've got some challenges. Just getting too many phone calls today. What I can do instead is say, okay, maybe I should look at the absolute value of AN. So what is that? The limit as n goes to infinity of the absolute value of AN is the limit as n goes to infinity the absolute value of 2 times negative 2/3 to the n. Again, the 2 can pop out, and you get limit n to infinity, absolute value, negative 2/3 to the n. Remember, absolute value is multiplicative. So this is the same as the absolute value of 2 times the absolute value of that, and the 2 is a constant multiple, so he comes out. The fun happens here. And don't worry, you won't have to do this every time you mess around with a geometric sequence. This will become 2 lim n to infinity, absolute value of negative 2/3 to the n, like this. And the absolute value of negative 2/3 is positive 2/3. So this is just 2/3 to the n. Does anybody know what this limit is? And could we argue why? I know Cody has an idea. Anybody else have an idea what this limit is?
Infinity.
What was that?
It diverges.
Infinity.
So the top, if you were to write this as 2 to the n over 3 to the n, the top and bottom both go to infinity. And unfortunately, even if we use L'Hopital's rule here, it wouldn't help us. But I want to draw your attention.
Set convergence.
I heard something else there. What was that last thought?
It looks like it converges.
Yeah, I agree. You guys remember when you first learned about exponential functions way back in algebra land? 2/3 to the n is equal to f of n, where f of x is 2/3 to the x. And f of x equals 2/3 to the x is a decaying exponential. Oops, sorry. It's a decaying exponential. We'll just do it like this. Whose graph always looks like this. Right? Just like e to the negative x, or 1/2 to the x. 2/3 to the x is a decaying exponential. It's decaying because the base is smaller than 1. So as x goes to infinity, so I'll just say, so limit x to infinity, f of x is limit x to infinity, 2/3 to the x is 0. So by our theorem relating sequences to functions of a continuous variable, this limit must be 0. Therefore, limit n to infinity, 2/3 to the n equals 0 also. Hence, lim n to infinity absolute value of an, which was the thing we were fucking with, which we found to be 2 times the limit as n goes to infinity of 2/3 to the n equals 0. Thus, when n to infinity an equals 0. So yeah, the original sequence that we were playing with here, 2 times negative 2/3 to the n, goes to 0. And the argument that we just went through would have worked for any geometric sequence whose common ratio is between -1 and 1. So let me recap. I'll hold here just for a second.
Can you explain why you related the lim n to infinity to f of x?
Yeah,
Was it
because
just so
I
we
don't
could
know
see
what this
clearly?
does, right? At this point, we don't know what the limit as n goes to infinity of 2/3 to the n is. We haven't studied sequences like this before. But we have studied functions like this before, right? This is a sort of function that I give my kids in college algebra to play around with when they're first learning about exponential functions. You learn way back in algebra land that if you have an exponential where the base is smaller than 1, that's a decaying exponential whose graph looks like this. So the logic here is to figure out this limit, I relate it to this function. This function, I know his graph. From his graph, I get his limit. And by our theorem, his limit has to be the same as the limit I'm looking for. Is that chain of reasoning coming through?
So you didn't plug in infinity for x in the
Correct.
limit.
Yeah, because
You just use the graph to see that it's approaching 0
exactly
with an asymptote.
Yes, perfect. Yes. So I don't know what this guy is. There's no algebra trick that will tell me what this limit is. But I do have a theorem that says if I can relate this to a function, then the limit of the sequence has to be the same as the limit of the function. So I go, okay, well, what would that function be? I just swap the n for an x. That function is 2/3 to the x. Do I know anything about that function? Oh yeah, in my algebra classes, I learned that if you have an exponential function where the base is smaller than 1, that's a decaying exponential. So its graph has to look like this. From the graph of this function, I can see that the limit as x goes to infinity of that function is 0. Therefore, by my theorem that connects the limit of this function to the limit of this sequence, the limit of the sequence has to be 0. Now I know the limit as n goes to infinity of 2/3 to the n is 0. And we had already seen that the limit I was looking for comes down to the limit of 2/3 to the n. And since we now know that the limit of 2/3 to the n is 0, I know that the limit of my absolute value sequence is 0. And if the absolute value of my sequence goes to 0, so does my sequence. I confess, it's a little bit confusing. But it's the most straightforward way to get at the result I'm about to share with you, which is the result that Cody referenced a second ago. So if that argument is boiling your brain a little bit, let me give you the full result, and then you can try to contextualize it a little, okay? So here's the theorem on geometric sequences. Theorem says the limit as n goes to infinity of r to the n can be broken down into a few cases. It's equal to 0 if the absolute value of r is strictly less than 1. It's equal to 1 if r is exactly 1. It's equal to plus infinity if r is strictly greater than 1. And your textbook, by the way, WebAssign says plus infinity is the same as DNE. But it genuinely does not exist if r is strictly less than 1. Strictly less than -1. So this is the full result on geometric sequences. Remember, any geometric sequence can be written as a constant times r to the n. So if you know what things like r to the n do, you know everything about geometric sequences.
Wait a minute, Professor. Wouldn't the does not exist cases fall into the first category? Because any absolute value of stuff that's less than -1 is just going to loop back around to 0, right?
If I will think about like -2. -2 is less than -1, right?
Yeah.
But the absolute value of -2 is 2, which is not less than 1. So
I see.
These are separate cases. If you want to, you can think of r being less than, having absolute value less than -1. This is the same thing as saying -1 is strictly less than r is strictly less than 1.
Okay. Yeah. All right. So if it was like -2/3, yeah, I see.
Exactly. So if you start close to 0 and you raise that number to greater and greater powers, it gets closer and closer to 0. If you start far away from 0 and you raise that number to greater and greater powers, it runs further away from 0. That's really what this is saying. How close do you have to be? You have to be within 1. So having absolute value less than 1 means you're between -1 and 1. You're within distance 1 of 0. Another way to say this is geometric sequences converge if the absolute value of r is less than 1. And in this case, they converge to 0. Converge if r is equal to 1. These are constant sequences. These are boring. They converge to the value of a0, whatever that constant was, and diverge otherwise.
Can I ask a question?
Of course.
So when we were doing improper integrals and we had, I forget which type it was, but it's when it was approaching infinity, it mattered how quickly the graph approached like 0 for whether or not it was convergent. That doesn't seem to be the case here. So like if I took r equals 0.9999, it's gonna approach 0 really, really slowly, but it'll still get there at infinity.
Yep.
So is that still convergent?
As a sequence, yes. The proper analogy for a type 1 improper integral is not a sequence, but a series. So with sequences, you should think of this as like finding horizontal asymptotes. A series is like finding an integral. So later we will talk about series. And when we want to understand kind of intuitively what it needs for what a series needs to converge, we need the general term of that series to approach 0 quickly. In the same way that for a type 1 improper integral to converge, we need the function to approach 0 quickly. But sequences are their own thing. They're not like integrals, they're not like series. They're genuinely their own thing. What sequences are most like is finding horizontal asymptotes. So that analogy, that idea of needing to go to 0 and go to 0 fast, that will be coming back. but it'll come back when we talk about series, not while talking about sequences.
Okay, that makes sense.
Cool. Yeah, okay. And we will get there soon. We will talk about that stuff next week. But for now, we're just finding horizontal asymptotes. And what we're saying is if you have an exponential function, that's what geometric sequences are. They're the sequence version of exponential functions. They will have horizontal asymptote 0 if the base is smaller than 1. They'll just stay 1 if the base is 1, and otherwise they'll like blow up or bounce around. So let's look at a couple more examples here, just to make sure we're all on the same page. So if I have the sequence 10 times 1/3 to the n, and again, here I'll say n is starting at 0. I know that the limit as n goes to infinity of an is the limit as n goes to infinity of 10 times 1/3 to the n is 10 times the limit as n goes to infinity of 1/3 to the n. And at this stage, I refer back to my theorem. R here is 1/3. The absolute value of 1/3 is less than 1. So that limit is 0. So this is 10 times 0, which is 0. Easy peasy lemon squeezy. So this sequence converges to 0. Or if I wanted to investigate the convergence of the sequence an, whose first few terms are, say, 1/8, 1/4, 1/2, 1, and so on. I would first want to find the pattern so I can find a formula for an. To go from 1/8 to 1/4, what am I doing? What's the pattern here?
Multiply by 2.
Yeah. So this is a geometric sequence whose starting term is 1/8 and whose common ratio is 2. So I can say an here is 1/8 times 2 to the n. So the limit as n goes to infinity of an is the limit as n goes to infinity of 1/8 times 2 to the n, which is 1/8 times the limit as n goes to infinity of 2 to the n. Here, r is 2. And since 2 is bigger than 1, this is going to plus infinity. So this is 1/8 times plus infinity, which is plus infinity. So this sequence diverges.
why can't we just say that it's times 2? Because aren't there other possible functions where these numbers would come out? Because we only have 4 numbers, so it could just be like a cubic.
Yeah, you make a fair point, right? Technically, you could find other sequences whose first few terms are this. But certainly the intent here is for this to be a geometric sequence. Anytime you're given like the first few terms of a sequence and asked to come up with a formula, there's always infinitely many correct answers. But I think the natural one here and the clear intention is that this is a geometric sequence in the same way that the previous guy where we had a, the 2, -2/3, blah, blah, blah. You can always interpolate with a polynomial of degree 4 or more and find many, many different things that could work. But what is intended here is definitely to treat this as a geometric sequence. But you're right, there are other sequences that have those first 4 terms. But I think that any other interpolation here would be kind of, what's the word? Contrived. If you wanted to say, no, this isn't geometric, it just happens to look that way. Really, this is some like, degree 5 polynomial that just looks like this for the first 4 values of n. Sure, you could find such a thing, but I think at that point we're being a little silly. The intent here is to get to this and then notice the limit. But you're right, you're technically correct. Yeah. All right, so this is geometric sequences. If you've learned about sequences in series before, do not confuse the two. If you're learning about them for the first time, I'll warn you right now, it's easy to confuse sequences with series. So keep straight in your head, the stuff that we're doing now is only associated with sequences. The rules for series are different. What else did I want to do? I think that's enough of these. How am I doing on time? Doing good still. Okay, so the other thing I want to talk to you about, recursive sequences, and then a connection to continuous functions, bounded sequences, and monotonicity. While we're here, I'm so sorry to do this to you, but Alexander, because you asked this question, here's a fun one. This has nothing to do with class. Find the next, 3 terms in the sequence 1, 1, 1, 2, 1. I promise you this problem has virtually nothing to do with class. I would never give you this as a homework or a test problem, but this is a cute sequence. It's got a special name. If you Google it, you'll find something. If you do that, don't spoil it for anybody else. Let anybody who wants to work on this work on it for a minute. It's a very silly sequence.
Is the next term 3, 1, 2, 2, 1, 1?
Fuck me. Yeah, it is. Yeah. Okay.
Well,
Alexander's got it already.
Can the next number be like anything? Like you can make multiple combinations of it.
Well, it is determined, but I'll tell you the rule is not algebraic. If you heard Alexander's answer a second ago, then that would come pretty close to giving it away. Yeah, if you want the next one here is this.
I saw a video about this exact sequence yesterday, so.
Oh, that's cute. Yeah, my calc professor gave me this. It took me about a week. So I'm pretty shocked that you had that right away. But yeah, it's a special sequence. It has a special name. It's got nothing to do with algebra, the definition. It actually has more to do with language than anything else. But just for fun, if you haven't seen it, play with it, see if you can figure it out. Okay, other sequence stuff. There's a special sequence, so special sequences. The most important one of these for you to get used to right now is called the factorial. sequence. We write this as an equals n factorial, like that. The exclamation mark is read as factorial. It's defined by the rule, I'm not going to write the A's. 0 factorial is 1. 1 factorial is 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. So 2 times 1 is 2, 3 times 2 times 1 is 6.
How is 0 factorial 1?
I know, I'll get there. A 4 factorial is 4 times 3 times 2 times 1. It's 1 because I say so. Is 24. I'll tell you a few different ways to reason yourself there in a little bit. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. So in general, n factorial, the way you compute the factorial of a number is by multiplying that number together with all the positive whole numbers less than him. All right, why is 0
on the gamma function?
Say that again, Alejandro?
I think we saw that on the gamma function.
Yes, we did. Yeah, this is exactly where we've seen that before. Yep, when we talked about the gamma function interpolates the factorial function. Gamma of x is the unique log convex function that agrees with the factorial on the integers. There are other, like Alexander was saying a minute ago, there are other functions that match up with sequences. But if you require the function to be smooth and log convex, meaning when you take the logarithm of it, you get something that is still like concave up, then the gamma function is the unique interpolating function for this. All right, why is 0 factorial 1? Well, because if you divide 5 factorial by 4 factorial, you get 5. If you divide 4 factorial by 3 factorial, you get 4. If you divide 3 factorial by 2 factorial, you get 3. If you divide 2 factorial by 1 factorial, you get 2. So when I divide 1 factorial by 0 factorial, I should get 1. And the only way that works is if you choose 0 factorial to be 1. Another interpretation or argument for why 0 factorial should be 1 is combinatorial in nature, meaning it has to do with counting problems. N factorial is the number of ways to arrange n plus 1 people at a circular dining table. So, you've got 7 people coming over for dinner and you want to know how many different ways can I seat them at the table. But I don't care about like rotations, I just care about who is whose neighbor. The number of ways you can do that is 6 factorial or 720. If I have just one person coming to dinner, how many ways should I be able to arrange them at the table? Well, there's just one motherfucker, so there's just one way to sit his ass down at the table. So 0 factorial should be 1. There's other ways to argue that 0 factorial is 1, but if you like, you can just take it to be the definition, or you can say because I said so, or you could take it to be what's called an initial condition in a recursion. And I'll show you what recursive sequences are in just a second.
Can you clarify? You said that you only care about who's seated next to who, is that correct?
Yeah. Yep.
So what if you flip the entire table? Because it's not rotated, but everyone's next to the same people, but it's...
So here's a table with 4 people, right? Alice, Bob, Joe, and Katie. If you look at Katie, Alice is to her left and Joe is to her right. This should not be double counted with Katie, Alice, Bob, and Joe, right? Because if you look here, Alice is still to Katie's left, Joe is still to Katie's right, and the same is true for all these others. So these should be equivalent.
So it's not just who they're next to, it's also left versus right.
Correct. Yeah, so rotation invariant. I suppose what you're saying is true. Yeah, it's not just who you're next to, it's who's on your left and who's on your right for everybody. So the number of ways to arrange these that are not equivalent, the distinct number of seating arrangements, or the number of distinct seating arrangements, would be 3 factorial, which is 6. And you can take the time to draw them out, you'll see. There's also a relatively straightforward proof. Like I choose where Alice is sitting. Then how many ways do I have to choose who goes here, right? So, well, there's 3 other people here. So I could pick any one of them to be on Alice's left, Bob, Joe, or Katie. Once I've picked this person, how many choices do I have to see who goes here? Well, it's either Katie or Joe. So I've got 3 choices for this, 2 choices for this, and after I've made those choices, there's only 1 for this. So 3 times 2 times 1, 3 factorial, which is 6. And then I don't care where Alice was sitting. If Alice was sitting here, it would be the same thing, right? Alice, and then 3 choices, 2 choices, 1 choice. So the number of, these are called cyclic permutations or 4 cycles. The number of 4 cycles with 4 objects is 4 minus 1 or 3 factorial. So there's a bunch of different ways to define the factorial sequence. I think the most natural one is just to show you algebraically this, right? So 0 factorial is 1, that's weird, but just deal with it, tuck it in your pocket. 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, 4 factorial is 4 times 3 times 2 times 1. In general, n factorial, we would say is n times n minus 1 times n minus 2. You know, you're just multiplying all the numbers beneath this until you get down to 3 times 2 times 1. This definition only really makes sense if n is like bigger than 6, you know, because otherwise I can't have these all as being separate things. So kind of a nicer way to say this is n factorial is equal to n times n minus 1 factorial, because this piece right here is n minus 1 factorial.
That breaks down if n is 0.
Say that one more time.
That breaks down if n is 0.
It does, yeah. So this works great for n greater than or equal to 1. And we have the initial condition, n greater than or equal to 1, together with defining 0 factorial to be 1.
So is factorial of negative numbers undefined?
Good question. Yes and no. Does most do this? I don't know if I've ever tried to graph the gamma function. We got here. This is not what we want. Oh, let me just try this. Yeah. Yeah, there we go. All right, so it'll graph gamma if I ask it for x factorial. This is pretty cool. At negative integers, you actually have vertical asymptotes. It's very weird. It's very, very weird. So
what is this coming from? I don't understand.
It's complicated.
It's also continuous at non-integer positive numbers, which
I was gonna say, is that impossible? Like, how can you do 3.5 factorial?
So that is where the gamma function becomes so important, right? This,
oh no.
Yeah, this is the curve that interpolates the factorial. This isn't really the factorial. This is graphing the gamma function. So let me show you something here. Gamma function, Wikipedia. Remember, when I introduced this to you guys, I showed it like this. I used the letter T instead of the letter X back when we were talking about integration by parts. the factorial is really only defined for n greater than or equal to 0, right? N has to be, so n factorial is only defined for integers that are greater than or equal to 0. All right, that's as a sequence. Remember, a sequence's domain is the natural numbers, or a subset of the natural numbers. So n factorial is really a sequence, and it only makes sense to talk about n factorial in this way if it is a non-negative integer. But for a lot of reasons, some having to do with combinatorics and counting problems, others having to do with number theory, mathematicians wanted a function that returned the same thing as the factorial when you fed it a positive integer, but also could be like differentiated and integrated and treated like a regular function instead of as a sequence. The first person to do this was Gauss, and he did it, here's Euler's. I guess Euler might have beat Gauss to it. He did it like this. And then Gauss, do they not have the Gauss one? The pi function? I don't see it here. Anyway, there's lots of different ways to define the gamma function. The main property of the gamma function is that it agrees with the factorial function on the positive integers. So is there any reasonable way to define 1/2 factorial? Not like this, right? That shit would not make sense. But is there a way to do it? Yes, using the gamma function. Does anybody know what 1/2 factorial is? Anybody want to guess?
Square root of 2.
Oh, we're close. Sort of square root of pi, actually. It's weird. It's so weird. I know it's weird. For our purposes, none of that weird shit matters. I'm just trying to get you guys comfortable with this thing as a sequence. So don't worry about the gamma function. Don't worry about what the fuck is gamma of 1/2. Just focus on getting comfortable doing algebra with this thing under the assumption that whatever's before the exclamation mark is a non-negative integer. But it is true that we can interpolate and build it into a continuous function, even an analytic function, and that thing is called the gamma function. It's very, very cool. But what I need you guys to get comfy with for now is just how to work with this thing as a sequence. And if you want to study the gamma function, there are lots of good books about it. The Wikipedia page is a great place to start. This is the definition that we played around with. And it's not terribly hard to show that, that this thing actually does spit out n factorial as long as you feed it z as an integer. But I'm showing you this because down the road, I need you guys to work with these things algebraically. So let me give you some examples of things that we can do. Where do we want to start here? How about this guy? I can look at the first few terms, and if you're having a hard time figuring out what a sequence does, it's wise to look at the first few terms. A 0 would be 1/0 factorial, which is 1. A 1 is 1/1 factorial, which is also 1. A 2 is 1/2 factorial, which is 1/2. A 3 is 1/3 factorial, which is 1/3 times 2 times 1, or 1/6. A 4 is 1/4 factorial, which is 1/4 times 3 times 2 times 1, which is 1/24. A5 is 1 over 5 factorial. Rather than writing it out, I'm just going to say it. It's 1 over 120. A6, 1 over 6 factorial is 1 over 720. So what are these numbers doing? Are they getting bigger? Are they getting smaller?
Smaller.
They're definitely getting smaller, right? 1, 1, 1/2, 1/6, 1/24, 1 120th, 1 720th. This is like 1.5 what is this? 0.16 as a decimal. I don't even know. Like definitely getting smaller and smaller and smaller, right? This is like 0.1. This is getting close to like 0.01. But if I wanted to show that the limit was 0, so this appears to be going to 0. To 0. How would I show it though? This is a good place for the squeeze theorem, if you remember the squeeze theorem. Zero is certainly less than 1 over n factorial. And 1 over n factorial is less than 1 over n for all n greater than or equal to 1. So the limit as n goes to infinity of 0 is less than or equal to the limit as n goes to infinity of 1 over n factorial is less than or equal to the limit as n goes to infinity of 1 over n. The limit as n goes to infinity of 0 is 0. The thing in the middle is what I'm trying to figure out. And the limit as n goes to infinity of 1 over n is 0. Therefore, by the squeeze theorem, the limit as n goes to infinity of 1 over n factorial must be 0. N factorial grows really fast. It grows faster than any polynomial. It grows faster than any exponential. So its reciprocal goes to 0 really fast. A neat fact. N factorial grows really, really fast. So fast, in fact, that the limit as n goes to infinity of b to the n over n factorial is equal to 0 no matter what you take b to be. So 2 to the n over n factorial. The top and bottom there both go to infinity. But n factorial gets so much bigger, so much faster, that even 2 to the n, which doubles every time n goes up by 1, that thing gets fucking big on its own, can't keep up. Can't even come close to keeping up. So much so that this ratio goes to 0. I can talk a lot about growth rates, and we can talk about Landau notation and big O notation, stuff like that. But for the purposes of this class, what I need you guys to remember is that n factorial is the fastest growing sequence we have. Grows faster than even the gnarliest divergent geometric sequences. So its reciprocal goes to 0 really fast. I want to work one or two other little problems here with the factorial And in service to that, we'll just do it like this here. Let me see, how are we doing on time? Are we getting close to that? Yeah, if you guys want to take a little break, we can take it's 1:58. So we'll come back at 2:08 to do lab, okay? And it's going to be a pretty short lab. I don't have a whole lot more for you guys, but I want to talk a little more about sequences, get a little more practice with factorials. So we'll take about 10 minutes and then we'll come back. All right, beautiful humans, let's start convening back here so we can finish up our discussion of sequences. I'm gonna get started in about 2 minutes. So if you're, doing whatever you're doing, just make sure you're back here at 2:10. We're gonna get started exactly at 2:10.
Hey, Professor.
Alrighty, so we are back. We're ready to get moving. Let's do it. So we now know what the factorial is. We have a pretty good idea of what sequences are, and we know a little bit about them. I have one more theorem for you, and that theorem has a fairly narrow application, but it's a worthwhile thing to understand. And then I want to introduce you to the application, the world of that application. So we're going to come back here talking about recursive sequences. Oh, was there something in particular you wanted to talk about, Alexander?
No, I was going to ask you an unrelated question before class started, but that's okay.
We got a second here if you wanted to ask something.
I just didn't know if you knew how to change your nickname on Canvas, because it's not letting me do it on my own, and so I have to contact like the Canvas admin for the school, but I don't think that is.
That's a good question. I don't know. But there might be a Canvas help dialog you can get into.
Yeah, I did that, and it said contact your school's Canvas admin, and I don't know who that is, so.
Oh, yeah, I honestly don't know. Probably someone at CAT, someone who works for the Center for Academic Technology, whatever. But yeah, I'm not too sure. But let's go ahead and come back, and I want to show you guys what recursive sequences are, and then I'm going to show you a theorem that is true of all sequences, but is especially useful for the recursive ones. So a recursive sequence is a sequence defined through a recursion relation and initial conditions. A recursion relation tells you how to get the next term as a combination of previous terms. And initial conditions tell you the first few terms. So the factorial can be thought of as a recursive sequence where an is equal to n times an minus 1. Together with the initial conditions that a0 is equal to 1, this actually defines the factorial sequence. Let me show you what I mean. Well, a0, they tell me, is 1. If I want to know what the next term is, A1, I follow this, which is the recursion relation. That would be 1 times A0. And since I know A0 is 1, this is 1 times 1, which is 1. A2, according to my recursion relation, would be 2 times A1. And since I know now that A1 is 1, this is 2 times 1, or 2. A3 would be 3 times A2. And since I know that A2 is 2, this would be 3 times 2, or 6. You see where this is going, right? A4 is 4 times A3, which is 4 times 6, which is 24. A5 would be 5 times A4, which would be 5 times 24, or 120.
So how do you find these values if you don't know the previous term? Like if you wanted n equals 100?
Yeah, that's the problem with recursive sequences. In order to get the next guy, you need to know the last guy. And sometimes you need to know like the last 2 or 3 or 4 guys. So the issue with recursive sequences is that if you want like A1000, you're probably going to need to compute A0 through A999 first. For this reason, computer programmers both love and hate recursive sequences. Recursive sequences are nice because they're easy to define, and they kind of sometimes are the most convenient way to describe certain behaviors. Like the next guy is the previous guy times n. That's kind of a nice way to describe the factorial function. But if I wanted, 70 factorial, it's going to be a pain in the ass to compute it with this formula. There is no good way. In short, Alexander, if you have a recursive sequence and you want to know, a term that's late in the order without computing all the previous ones, there's no convenient way to do that. There is a tool for solving recursion relations to find the algebraic formula for a recursive sequence. That tool is called generating functions, and they're well beyond the scope of this class. But if you're interested in that, I'm going to do this again. You guys are getting a bunch of Google Drive links today. If you want to learn how to solve recursive sequences for explicit algebraic formulas, this is this book, which is Miklos Bona's A Walk Through Combinatorics, has a chapter on generating functions that is very good. So if you're interested, counting problems. Wonderful book, but again, well beyond the scope of this course. What I'm here to show you guys is just how recursive sequences work, and a little bit when we can tell they converge. So the factorial is one example. The most famous example, though, is the Fibonacci sequence. I'm going to use the symbol Fn here. The nth Fibonacci number is what you get by taking the previous 2 Fibonacci numbers and adding them up. So here you need 2 initial conditions. I have to tell you that like F0 is 1 and F1 is 1. Kind of as many things as you have here, previous terms, you need that many initial conditions. So if I wanted F2, the second Fibonacci would technically be the first Fibonacci plus the 0th Fibonacci, which is 1 plus 1, which is 2. F3 would be F2 plus F1, which is 2 plus 1, which which is 3. F4, the fourth Fibonacci number, would be the third Fibonacci number plus the second Fibonacci number, which is 3 plus 2, which is 5, and it keeps going like this. The fifth would be the fourth plus the third, which is 5 plus 3, which is 8. The next one is 13, and it keeps going like this. Here, these guys, clearly, Fn here grows bigger and bigger. So it's not likely convergent. In fact, the term for this, growing bigger and bigger, I have to be a little bit careful, but this means unbounded. Doesn't stay smaller than any fixed constant. Right, so an unbounded sequence is one that, you know, you pick your favorite number, whatever your favorite big number, like 10,000, eventually the Fibonacci numbers will get bigger than that. Because you just keep adding things up, right? And the things you're adding up are themselves large. You know, you add 5 plus 8, you get 13. You add 8 and 13, you get 21. You add bigger and bigger and bigger stuff, and it just keeps getting bigger and bigger, specifically without bound. So this guy, so the Fibonacci sequence, and if we want to refer to it as a singular thing, remember we put it in braces like these, n equals 0 to infinity, is unbounded and thus divergent. You may remember from the start of class, one of the things I kind of pointed to in Rudin was that theorem that said if a sequence is convergent, then that sequence must be bounded. There are plenty of bounded sequences which are not convergent, but let me go ahead before I talk anymore and just say what it means for a sequence to be bounded. It's the exact opposite of unbounded. So these are recursive sequences. There's lots of them out there. I'll show you some more in a little bit.
Professor, I have a question.
Yeah.
Might be a little bit unrelated, but I was taking a look at the book and it said something about the Fibonacci sequence and the many uses that you could do on the world with it, right? One of them caught my attention, and it's predicting the what do you call it? The markets, right? So, you know anything about that?
I don't know. The Fibonacci sequence shows up in a lot of places. Generally, anytime you have what's called a stochastic process, where the thing that happens next depends on what happened before, you can usually find some relationship to a recursive sequence there. One of my favorite problems involving the Fibonacci sequence asks, you know, if you have a set of n stairs in front of you, a staircase with n stairs, and you're able to take like steps of 1 stair or 2 stairs at a time, like we all do this, right? Sometimes when you're going up the stairs, you do them 1 at a time, you do them 2 at a time, sometimes you switch back and forth. How many ways can you climb a set of n stairs taking steps of size 1 or 2? Turns out to be the nth Fibonacci number. But I'm not personally aware of any direct connection to stock markets or anything like that, although I wouldn't be surprised if there are some models that include that.
Are you familiar with the Tower of Lyre?
Tower of what?
Lyre, L-Y-R-E.
Is that real? Maybe. Oh yeah, this is a little bit different. Yeah. This is one of the ways to show that the harmonic series diverges. Is there a connection to the Fibonacci sequence here too?
Oh, not to my knowledge. It just seems kind of related, I thought. Like it seems like it's another recursive series.
There is
Maybe?
a sense here in which there's some recursion going on, but this is a little bit different. Following, so I don't know if you guys have seen this question before. The question is like, if you have the side of a desk here, where can I, yeah. If you have the side of a desk and you want to start stacking like bricks on top of it, how far can you go before the thing falls over? Can you extend as far out as you want without the thing falling over? It turns out the answer is yes. You can go as far over as you want, and it's related to the divergence of a certain series. Now that's not directly related to anything that we're talking about, but it is cool stuff. There is, I think there is, where is this? Tower of Hanoi. I think this relates to the Fibonacci numbers in a neat way. If I remember right, there are logical analysis, recursive implementation. I think there is a way to relate these things to the Fibonacci numbers, but there's lots of cool ways to do this. It looks like this is our recursion. So you need some modified Hanoi Tower problem to get what we want if we want Fibonacci numbers. But anyway, I want to stay focused here so we don't go too long because I actually have to run to a doctor's appointment not too late. Bounded sequences. So a sequence AN, and it could start wherever. I'll say n from 0 to infinity, but it could start at 1 or 5, is called bounded if there is some number m such that the absolute value of an is never larger than m, say less than or equal to m for all n. Right, so if a sequence that doesn't run off to infinity is called bounded. Specifically, we can get a little bit more ornery about this. A sequence AN is bounded above if for some number m, AN is no greater than m for all n, and a sequence AN is bounded below if for some number m m is less than or equal to an for all n. Graphically, what this means is that the graph never goes above a certain point. That means bounded above. All right. Yeah, I'll just draw this in as a solid line. This is what it looks like for a sequence to be bounded above. It could jump around. It could come back down, but it's just never allowed to go over that line. This is what it looks for a sequence to be bounded above. And for a sequence to be bounded below, you know, m could be positive, it could be negative, doesn't really matter. Just means that the terms of the sequence never dip below that. All right, so this is bounded below. So a bounded sequence is a sequence that is bounded above and below. Right? It means that the sequence never gets too big, does not run off to infinity. It turns out, it is true, that every convergent sequence is bounded. it's worthwhile for you to think about why that's true. But sort of the reason I'm showing you this definition is to show you a theorem. And this theorem is pretty cool. I guess before I do that, let me just give you some examples. Example, an equals 1 over n, where n is greater than or equal to 1. This is bounded, right? Because 1 over n is bigger than 0, and as long as n is greater than or equal to 1, it's less than 1 for all n. So it's bounded below by 0. And it's bounded above by 1. And we know that this is actually a convergent sequence, right? The limit here is 0. Another example of a bounded sequence the sequence an equals -1 to the n is bounded. It's bounded below by -1, and it's bounded above by +1. Right? This sequence is just 1, -1, 1, -1, 1, -1, 1, -1. So it never gets smaller than -1. It never gets bigger than +1. So this is also a bounded sequence. The sequence an equals n squared is bounded below, but not bounded above. Right? We know that 0 is less than or equal to n squared for all n, but there is no number m such that n squared is less than or equal to m for all n. Eventually, n squared will get bigger than any number m you choose. So pick your favorite fixed constant m equals 1,000,000, whatever. Eventually, n squared will get bigger than m. Eventually, this will be broken. There is no number m such that n squared is less than or equal to m for all n. All right, why are we talking about this? Well, there's this theorem that says bounded monotone sequences converge. So bounded, we know what bounded means. Monotone means always increasing or always decreasing. Specifically, increasing sequences bounded above must converge, and decreasing sequences bounded below must converge. I'm not going to offer a technical proof here because the technical proof is a little bit technical, but I'm going to give you a picture proof that I think will probably suffice to convince you. Suppose the sequence AN is increasing and bounded above, say by the number n. Well, okay, here's m, and the graph of my sequence it's always increasing, right? So my graph is always going up, but then something happens. It's not allowed to go past m. It's increasing, so it always has to keep going up, but it's not allowed to go past this line. That means the dots have to start piling up on this line. It's got no other choice. So it has to converge. If all the dots start piling up on this ceiling, where have you seen this picture before? When we talked about the definition of convergence. And similarly, if you're decreasing and bounded below, the same thing happens, just flip the picture over. So bounded monotone sequences, bounded monotone sequences, come on, goddammit. Bounded monotone sequences have to converge. There's no way that you can keep increasing and not start to pile up on this ceiling. I'm not allowed to turn around and go back down, but I'm also not allowed to poke through this ceiling. That means that all the terms of my sequence have to start piling up on this ceiling, which means that the sequence converges to this value, which would be called the least upper bound for that sequence.
Would we say that like a sine curve is bounded at plus and minus 1?
Yes, sine is indeed a bounded function. One of the things that I'm kind of like inserting here and hoping you guys will think about is this is a bounded sequence, right? In the same sort of way that sine is bounded. It's bounded between -1 and 1, but it's not convergent, right? This is a bounded but divergent sequence. Sine n would also be a bounded and divergent sequence. So in order for a bounded sequence to be divergent, it must not be monotone. It must be allowed to go back and forth. And in order for a monotone sequence to diverge, it must not be bounded. It must be able to break through any ceiling. So these are the sort of logic games that we want to get comfy and have fun playing. So bounded monotone sequences converge. Here's the last thing I want to show you. Consider the sequence I'll just write it like this: square root of 3, square root of 3 times the square root of 3, and then the square root of 3 times the square root of 3 times the square root of 3. and so on. The square root of 3 times the square root of 3 times the square root of 3 times the square root of 3. And so on. AN here is equal to the square root of 3 times AN minus 1, with a 0, say, equal to the square root of 3. So A1 would be the square root of 3 times A0, which is the square root of 3. So this is A1, right? This is A0, this is A1. A2 would be the square root of 3 times this. This is an increasing sequence. If you take some number and multiply it by 3, it gets bigger. And when you take the square root of that, it will still be bigger than the thing you started with, because your first step was multiplying by 3, and taking the square root never kills you as much as multiplying by 3 makes you bigger. So AN here, the sequence, the recursive sequence AN defined above is monotone increasing. It's harder to show, but it is true that AN is bounded above. We can compute some of these terms here. Let me give you a feel. And if we keep going like this, you'll see that these are always bounded above by 3. Proving either of these things is a little bit tricky. And for that reason, what I'm showing you here is kind of silly. They don't make for very good problems unless I tell you that these things are bounded and monotone. But what I want to show you how to do is to calculate the limit of such a sequence. So what I claim is that if you take an infinite nesting of square roots of 3 like this, that actually converges to a particular finite number. Here's how you would figure it out. So to find the limit of a convergent recursive sequence, and I know that this sequence is convergent because it's monotone and it's bounded, take limits everywhere in the recursion relation. So I'll take limits everywhere in this expression. Lim n to infinity of an is equal to lim n to infinity of the square root of 3 times an minus 1. This is like saying a infinity equals the square root of 3 times, well, as n goes to infinity, n minus 1 also goes to infinity, a infinity. So if I call that thing L, let lim n to infinity an be L, then we get L equals the square root of 3L. And now you can solve this for L. That'll give you L squared equals 3L, which is equivalent to saying L squared minus 3L equals 0, which is equivalent to saying L times L minus 3 equals 0. So L equals 0, or L is equal to 3. Now, if you look at the first few terms of the sequence, it starts at something a little bit bigger than 1, and it keeps getting bigger and bigger. So L can't be 0. L has to be 3. So if you take this infinite nesting of square roots of 3, you actually get 3. Let me show you a little more, right? So you see what these numbers are doing, right? They're getting closer and closer and closer and closer and closer to 3. It's a fun thing, and this isn't an easy thing to sort out algebraically, right? There's no nice way to write these algebraically. You could try to break them down as powers. It's not impossible, but then you're going to end up with this infinitely long product of really weird powers of 3. It's not a pretty thing. And this is just one example of a recursive sequence whose limit you can crunch out if you assume the limit exists. And the big deal is everywhere there's an an or an an minus 1 or anything like that, you just swap in L. Assuming that the limit exists, this would have to go to L and this would have to go to L. I called it A infinity here to try and think about it in a way that might be less confusing. But if you want to, you can jump straight from this line to this line. So this is how we solve for limits in recursive sequences. And there is 1 or 2 problems like this in your homework. Here. And this is just the last little thing I wanted to show you. So most of the rest of this is not going to be challenging. It's all just algebra basic stuff. No, that doesn't work. No. The big goals for you guys right now are going to be to keep the theorem straight, get comfortable with the language, get comfortable with the algebra of factorials, and that's pretty much it. This last thing here is more or less just a fun thing, but it is a lot of fun. So you've got some terminology. Here you've got a recursive sequence, and they want you to just list the first few terms. This looks like a geometric sequence to me. They want you to find a formula for an. You've got lots of things like that. A few things dealing with ratios of factorials. This is good stuff. So you need to practice simplifying this sort of expression and really work this out. Spend time on this on your own before asking for help. I promise it's not that hard if you think about what each of these things represents. But you should think about it for a while and then take the limit. The rest of this is all pretty trivial. This is a L'Hopital's rule thing. So there are a few squeeze theorem and L'Hopital's rule thing. So for this, you're going to need to use L'Hopital's rule. And if you don't remember how to use L'Hopital's rule for indeterminate powers, you'll want to go back into section 2.6. And then there are a few other things here to do with recursive sequences. Yeah, here's the one that I was just showing you. So let's see, is there anything else that I wanted to show you guys today? Not really. I'll say this, when it comes to the indeterminate power stuff, does anybody remember, so we're changing gears here, does anybody remember this limit? This is something we should have seen back in Calc 1, probably also saw it in algebra classes, but it gets brushed under the rug pretty quickly. So the base on its own is getting closer and closer to 1, right? If I put a bigger number down here, that base will get closer and closer to 1. But then if I raise it to this power, anybody recognize those first few digits? Oh, I see there's something in chat here. Yeah, what is this the first few digits of? Good, it's E. Yeah, Matthew sent it to me in chat. This is E. The way you figure something like this out, first, when you plug in, this looks like 1 to the infinity, which is an indeterminate power. The way you figure something like this out is you just call it L. You say L is equal to the lim as x goes to infinity of 1 plus 1 over x to the x. And you take natural log on both sides. You can push the natural log inside the limit. I'll write it like this at first. Then the limit comes out of the log. And now you've got the natural log, I should write it like this, natural log of 1 plus 1 over x to the x. That's the same as lim x to infinity x times the natural log of 1 plus 1 over x. Powers can come down from the inside of logarithms to the front, right? This is one of our rules for logarithms. If you try plugging in now, this looks like infinity times ln of 1, which is infinity times 0. This thing is called an indeterminate power up here, and this thing is called an indeterminate product. The way we handle indeterminate products is to turn them into indeterminate ratios and then apply L'Hopital's rule. So this is lim x to infinity, ln of 1 plus 1 over x divided by 1 over x. I take this x and I shove it downstairs as a 1 over x. And if you look at this now, this looks like ln of 1 divided by 1 over infinity, which is 0 over 0. This is now an indeterminate ratio, which means from here, I can apply L'Hopital's rule. I'll still have my limit as x goes to infinity. L'Hopital's rule says take the derivative of the top and the derivative of the bottom, and then try again. The derivative of the top is 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x. It's a chain rule thing. You differentiate a natural log, you get 1 over the inside times the derivative of the inside. And downstairs here, the derivative of 1 over x is negative 1 over x squared. So if we finish simplifying the top, I get 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x. The 1 differentiates to 0. The 1 over x differentiates to negative 1 over x squared. And now we can cancel these guys. send x to infinity, and I get lim x to infinity, 1 over 1 plus 1 over x. Everything else is gone. That's 1 over 1 plus 0, which is 1. So what we've just shown here is that the natural log of L is equal to 1. If the natural log of L is equal to 1, that's the same thing as saying L itself is e to the 1, or e. You have a limit like this in your homework and you need to go through it. It's given in terms of n, it's given as a sequence. So your very first step on that sequence problem is going to be to relate it to a continuous function, like this, right? And then you can apply L'Hopital's rule. That's the only sort of challenging thing as far as like algebra challenges in here that I think you guys should be aware of. So if you didn't practice this well back in Calc 1, and I know not everybody does, here is an example that you can follow as you're working through, what problem is it? You will want to follow this as you solve number 20. Right? You want to take the limit as n goes to infinity, and this expression, you notice that looks an awful lot like this. So you're going to follow this exact same procedure for number 20. Right? And then down the road, I will give you guys a kind of cheat code for these things, but you need to know how to work them out. You need to go through this process. You're going to need to do it a minimum of twice. You're going to do it once for this homework, and then you're going to do it once a little bit later to prove the sort of cheat code I'm going to show you. But that is it. That's where I was planning to leave things for today. Do you guys have any questions on this example for me? Any other burning questions to do with sequences or the stuff we've been talking about this week at all?
Not from me. Have a great day, Professor.
Okay. Anybody else? Thank you, Ethan. Anybody else?
When are we going to go over surface areas of volumes of solids of revolution?
So volumes of solids of revolution.
Yeah, I didn't mean volumes. I meant surface area, sorry.
Yeah, arc length and surface area, we're going to talk about when we talk about chapter 10. So after we do sequences in series, we're going to look at parametric equations. And it turns out that's really the best place to talk about arc length and surface areas. And I'll connect it back to the chapter 8 stuff at that time. But that'll all be right after we finish Taylor series and Maclaurin series. Any other questions? Alrighty, then you guys are free to go. I hope you have a wonderful weekend, wonderful rest of your week. Please do work hard on this homework. I set the due date for next Thursday because I know it was late getting open, but get in there as soon as you can, start working on it. This is somewhat tough stuff. And the better you understand 11.1 and 11.2, you can minimize the pain that you'll be feeling down the road. Sequences and series are tough. So put the time in now while we're doing foundational stuff. It'll pay off later, I promise. All right, take care, guys.
All right, have a great day.